Welcome back. This is part 5, the final part of this mini course. And here I'm going to concentrate on the low temperature region of the Ising model and show you how to prove that the spontaneous magnetization is non-zero. Okay, the proof is based on the beautiful idea, the argument developed by Professor Piles. And this proof, mathematically rigorous proof is due to Professor Griffiths and Professor Dobrushin. And I like this proof very much. And of course, it's mathematically rigorous, but it also contains beautiful physical idea. Okay, and I hope you will enjoy it. Okay, so again, let me start by reminding you the main theorem that I'm going to prove here. So this is our third theorem, but it's called theorem 5 because we prove it in this theorem, prove it in this part 5. Okay, it says that there is a constant beta L such that for any beta greater than beta L, this spontaneous magnetization is strictly positive. And we also see that as beta goes to infinity, that means the temperature goes to 0, this spontaneous magnetization goes to 1, which is the maximum possible value. Okay, so as before, I will first state the basic lemma. And by assuming this basic lemma, I will prove this theorem. It's easy. Okay. So what does this theorem say? Well, it says, first of all, we can set beta L to be 0.7. Okay, this is just an arbitrary, this is just a convenient number. So there's nothing deep about here. So anyway, this is sufficient for our proof. Okay, and then for any beta greater than or equal to beta L, there exists a function, a strictly positive function of beta that we call mu beta, such that this expectation value is lower bounded by mu beta for any u and for sufficiently large L. So what is this? Well, this is the expectation value of sigma u under the plus boundary condition in the system with size L, and our inverse temperature is beta, which satisfies this, and the magnetic field is 0. Okay. And we also have that this mu beta approaches 1 as beta goes to infinity. Okay, so anyway, let's assume this and prove this. But this is very easy. Okay, as we have seen many times, if you differentiate this finite volume free energy density with respect to h, and then you get this minus of the expectation value of the magnetization density. Okay, and then since this is lower bounded like this for any u, we see that this is upper bounded by this. Okay. Now, we know we have proved the concavity of f for any boundary condition, so this is valid. Okay. And then this shows that this first derivative is non-increasing in h. So this means that for any h, which is larger or equal to 0, this thing can never be larger than this. So this is also upper bounded by this. Okay, good. So we have this very elementary, and then we assume that h is strictly positive, and of course beta is larger. Well, this could be larger than or larger equal to. But anyway, we assume this and look at this difference. Okay, and again, we can represent by this like this. We differentiate and integrate. Okay, and then we know that this is upper bounded by minus mu beta for any h prime, which is positive. This is then you plug this in. Then the integration is trivial, and you get this. Okay, since h is strictly positive, we can divide this by h to get this. Okay, and this is for finite volume free energy density under the plus boundary condition. Okay, so this works only because we are using plus boundary condition. And now, but we take this limit, the infinite volume limit, the thermodynamic limit. And then we know that the limit exists. And also, very importantly, the limit is independent of the choice of boundary condition. So we get this universal free energy density that is independent of the boundary condition. And this thing satisfies this. Okay, well, we are almost done. This is MSB, the definition of spontaneous magnetization. This is the right derivative. But anyway, this satisfies this. So we see that this thing is lower bounded by this, and this is strictly positive. Oh, okay, this one is lower bounded by this, but of course, the same bound is true if you let h go to 0 from above. Okay, so we are done. So we have proved this theorem 5, assuming this basic lemma. So our main task is to prove this lemma here. Okay, so before going into mathematical proof, let me just give a very brief idea under the proof. So this is due to Professor Piers, and it's called the Piers argument. So let's look at the system under zero magnetic field, and suppose that the whole system is filled by O plus. So we have this C of plus, and we ask whether this C of plus is stable or not. And we are interested in whether the system exhibits ferromagnetic order or not. So this stability or instability of C of plus, the C of plus is crucial. Okay, so let me start from one dimension. And in this case, we know that there's no ferromagnetic order except in zero temperature. Okay, in the zero temperature, in the strict zero temperature, I mean the ground state, we have either plus 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 or minus 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 as ground state. So we have ferromagnetic order. But we are at a very low but still non-zero temperature. Okay, so here is the C of plus, and here is a small island of minus. Okay, and I assume that this island contains a fixed site, which is yellow site. So I assume that this island contains n spins like this. And I ask, what is the energy cost of this island? Okay, and we have this ferromagnetic interaction sigma sigma. So here the energy is -1, and this bond energy is -1. Here also -1, -1. But here on this pink place, we have this here. It's plus and minus. So the interaction is +1. Okay, so here you get extra energy +2, and here also you have extra energy +2. So the total energy cost of having this island is 2 + 2, or 2 by 2, and it's 4. So we have this penalty e to the -4 beta from the Boltzmann factor. Okay, so this is small, but does this kill this small island? But one thing we have to note is that this penalty is independent of this size of the island. Okay, so this is a small probability, but if you are lucky or unlucky enough, you will see this kind of event. And one thing is that this n can be as large as you want, but this penalty doesn't change. So this roughly means that there's no ferromagnetic order. Okay. Now, the essence is more important thing. This is a sloppy discussion, but anyway, it is true that there's no ferromagnetic order at non-zero temperature in one dimension. But the physics is totally different in two dimensions. So now this is the C of plus in two dimensions. So this the whole plane is basically filled by plus, and this is a fixed site, and we have this island here. So I suppose that this island is surrounded. The border of the island consists of L bonds. Okay, and I again ask, what is the energy cost? Okay, and then for each pink bond, we have to pay extra energy +2. So the total energy cost is 2L, and so the total penalty is e to the -2 beta L. And one thing you have to note is that this penalty gets smaller and smaller, or the penalty gets harder and harder. So this factor becomes smaller and smaller as L grows. This is an essential difference. Okay, but this is the this is taking into account only the effect of energy. But we also have to take into account the effect from the entropy. So the possible number of configurations. So very roughly speaking, we will have much more rigorous discussion later in this part. But very roughly speaking, we see that the patterns of this island is roughly 3 to the L. So if you multiply these two factors, this combines the energy effect and also the entropy contribution, and we get this. Okay, so this shows that if beta is large enough so that this 3 times e to the -2 beta factor is less than 1, then this means that this factor gets smaller and smaller as L grows. So this says that the large L, the island with large L, is suppressed, even if you take into account the contribution from the entropy. Okay, so of course, so this roughly tells you that within the sea of plus spins, of course there appear some small islands, but their size cannot grow indefinitely. So they will have some fixed size, and you will see islands here and there, but they will never grow. If provided that that beta is sufficiently large, that means we are in sufficiently low temperature. Okay, so this shows that the ferromagnetic order, this suggests that the ferromagnetic order in the two-dimensional Ising model is stable if beta is large enough. Okay, so this is the basics of Pyre's argument, but we want to make this into mathematically rigorous proof. Okay, so here we only considered one island, but of course we have to consider the whole plane and all possible spin configurations. Okay, so we are going to do that. Okay, before going into this proof, let me introduce a fancy notion called the dual lattice. But this is just a simple thing. And these are something we already know. So lambda L, these are definition of our lattices and the sets of bonds. Okay, so this is our standard lattice, like this, consisting of L squared sites. And so this is a corresponding set of bonds. It consists of pairs, unordered pairs of neighboring sites like this. So these blue segments denote the set of this. And then we also define this larger lattice, which in which case it consists of these 25 sites. And this is a boundary. If you take away the sites from the original site, then these remaining sites are called a boundary. Okay. Now, I also define this B bar L, the corresponding large set of bonds. And this is basically the set of bonds within this lambda bar, but we exclude those bonds in which both sides live on this boundary. Okay, so we do not consider bonds like this. So we basically consider bonds, the original bonds in this B, and also these extra bonds sticking out of this original smaller lattice. Okay, anyway, these are things we already know. Okay, now I will define a dual site. Dual site is a point taken at the center of each placket, which means unit square in the original, in this larger lattice lambda bar L. So here is a placket, it's a square, and so I take a site at the center, a point at the center. This is a dual site. And of course, this is also a placket, so I take a dual site here. So dual sites are like this. Okay, but anyway, I already have a picture here. So these green dots denote dual sites in this case. Okay, and by lambda L star, I denote the set of all dual sites. This is sometimes called dual lattice. Okay, and what are dual bonds? Well, you can say that, okay, you can say that, okay, dual bonds are bonds connecting two dual sites. Okay, that's okay. But let me define it in this way. A dual bond is a bond that crosses a original bond in B bar L. So this is the original bond in B bar L, and then dual bond has the same length, and they cross at the center, and they are orthogonal with each other. Okay, so this is our dual bond. So here, so for this bond, this is dual, 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 this is dual. Okay, and so these, well, these green, orange lines represent dual bonds. Okay, and again, I denote by BL star the set of all dual bonds. Okay, now this is too complicated, so let me just draw these green dots and yellow bonds, and here it is. So this lattice is lambda 3 star, the dual lattice, and these orange lines form this B3 star, the set of dual bonds. And from this thing, you see that this is identical to lambda 4, right? This is 4 by 4 square lattice. And so this is identical to B4. So in general, lambda L star is identical to the original lattice lambda L plus 1, and BL star is identical to BL plus 1. Okay, anyway, this is just a definition, but it will become useful later. Now I will really start the proof. So I will first consider a representation of Z plus L. beta 0. Okay, so we have 0 magnetic field. We consider plus boundary condition, and the system size is L. Okay, so this is our Hamiltonian. So since we have 0 magnetic field, no magnetic field term here. Okay, and this is sum over all bonds in this B bar L, larger set of bonds. Okay, and we have sigma u, sigma v. So if bond is like here, and then there's no problem. U, v are here, so sigma u, sigma v are determined by this spin configuration. But this, if you take a bond like from here, then if this is u, this is v. So you have sigma v, which is outside of this. So the rule is that whenever you see sigma v from this boundary, we understand that the sigma v is set to be 1. Okay, this is what we mean by the plus boundary condition. Okay, so other spins are free, determined by this sigma, but the spins at the boundary is fixed to be plus 1. Okay, so now this is our partition function. This is a usual definition, e to the minus beta h. So sigma is just summed over all spin configuration here on these black sites. Okay, and these spins are fixed as before. And so here, well, we have sum over this exponential. Then you can pull this down and make it into product. So this is equal to this product. Okay, so this is again product is over all bonds in this B bar. And then this is very easy thing. I want to rewrite this in this way, so I put extra e to the minus beta here. So to compensate this, we have to put this here. Again, so here's this count the total number of bonds here. As before, whenever I have a finite set S, then this denotes the total number of elements in this set S. Okay, so in this case, this is the total number of bonds here, 1, 2, 3, 4. I don't want to count. Anyway, this is irrelevant for our analysis. Okay, so anyway, it's here. It's just a trivial factor. All right, so now let's look at this quantity here. Okay, so we have this e to the beta sigma sigma minus 1 factor for each bond. Okay, and on each, and recall that sigma is either plus minus 1. So this product is, of course, either plus minus 1. Okay, suppose that this is plus 1, and then this 1 minus 1 is 0, so you get 1. Okay, so 1 if sigma u is sigma v, sigma u times sigma v is 1. Or a different way of expressing the fact that sigma u times sigma v is 1 is that sigma u and sigma v are the same. Okay, but anyway, you don't have to get, anyway, this is another way of saying this. And since this is a ferromagnetic system, two spins on the neighboring two spins wants to point in the same direction. And in this case, they are pointing the same direction, so they are happy. So in this case, this is jargon in this field. So in this case, we say that, okay, this bond, UV, is happy because sigma u and sigma v are the same. Okay, suppose that sigma u and sigma u times sigma v is minus 1, which means that sigma u and sigma v are different. In this case, this bond is unhappy because two spins on the bond is pointing in the different direction. Okay, so in this unhappy situation, this is minus 1, so this becomes minus 2 beta. So this factor becomes e to the minus 2 beta. This is the penalty that we discussed before. So this is big and this is very small. But this is natural because the system wants all bonds to be happy. But we unfortunately had this unhappy bond, but it has small weight. Okay, it's quite natural. But anyway, so this is just a trivial rewriting. And then we can rewrite this, again, not trivially, like this. So what is this? Well, this U of sigma is the set of unhappy bonds. Okay, so given the spin configuration, you can decide whether each bond is happy or unhappy. So this is a condition for unhappiness. And so we just pick up all these unhappy bonds, and that's U. And then this counts the total number of unhappy bonds. And why is this? Well, this is just trivial. So here you take product of all these things. So when the bond is happy, you just have 1, and whenever you have unhappy bonds, you have e to the minus. So you just count the number of unhappy bonds, and e to the minus 2 beta times okay, e to the minus 2 beta times the number of unhappy bonds. Okay, so this is the number of unhappy bonds. Okay, so this is a representation, but this is not very non-trivial. So this is rather trivial. This is almost a straightforward rewriting of this. And still, this is not a stochastic geometric representation. We still have some overall possible spin configurations. Okay, so I want to make this into a stochastic geometric representation in the next step. So we shall define a set of dual bonds that correspond to this set of unhappy bonds. How do you do this? Well, so we shall use this notion of dual bonds here. Okay, so here we have some spin configuration, plus, minus, plus, minus. So of course, everything at the boundary is fixed to be plus. And then I will see which bond is unhappy. So these pink is not a very unhappy color, but these pink bonds denote the unhappy bonds. Okay, so this is plus, okay, this is plus plus, this guy is happy, minus minus, it's happy, but this is unhappy. Okay, then for each unhappy bond, you draw its dual bond, these green bonds. Okay, you know that this is unhappy, and then I draw this green thing here, 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 here. Okay, you do this for all these unhappy bonds. And then you just concentrate on this green thing. Okay, then this is set of dual bonds. So this set of dual bonds is denoted by C of sigma, and this is of course a subset of BL star. Okay, BL star, this is the set of all dual bonds. Okay, so starting from a spin configuration, we constructed this set of unhappy bonds, and from this set of unhappy bonds, we constructed this set of dual bonds, C of sigma. And now I claim that this C satisfies this very important relation. The boundary of C sigma is always empty. What is the boundary? Well, this is something we have already seen in part 4, the previous part. So the definition is exactly the same. In that case, we discussed the boundary of B, but now it's the same thing on the dual bonds. Okay, and so C is for any C which is a subset of BL star, we denote by NC U star the number of dual bonds in C that contains a dual site U star. Okay, and then this boundary of C is defined as a collection of U star, the dual sites, at which NC U star is odd. Okay, so I claim that this is empty, but this should be clear from this picture, isn't it? Because whenever if you have some elements of DC boundary, then it means that you have this kind of open ends in this thing. But look, this C is constructed in this way, and this is nothing but the boundary between plus region and minus region that we have seen in the very introductory part. Okay, so this is a boundary of the C of minus, no, the island of minus spins, right? So the boundary can never have endpoints. Boundary always have to form closed loops like this. So it's just clear that this is valid. Okay, so you can prove this in this way or graphically, but here is a rather formal proof. This is not very interesting, but this is a short proof. Okay, okay, so let's take this. Let's look at this dual site U star, and so these are original sites. So it's surrounded by 4 original sites, U1, U2, U3, 4, like this. And spins live on these original sites, of course. And so for any spin configuration, I consider this product, okay? Sigma U1, this product of this thing, and so this from here, here, here. But if you look at this, you have 2 sigma U2. So this product is just 1. This is 1, 1, 1. So anyway, we have 2 of them. And the product is always 1. So what does this mean? Well, each of them can be plus minus 1, plus minus 1, plus minus 1, plus minus 1. If the product is minus, then that bond is unhappy. And then this can be either plus minus 1, but the product should be 1. this means that the number of -1 can be 0, no -1, all plus, or there are only 2 -1, or 4 -1 in order to satisfy this. So this means that the number of unhappy bonds is always even, 0 to 4. And so then by definition, this is always even, and this is empty. Okay, so that's a proof. But rather than looking at this proof, I think it's better to look at this kind of picture, or you draw your own picture by yourself to convince yourself that this is always the case. But this is very essential. Okay? Right, so we have this thing. So this from this we see that there is a one-to-one correspondence between the spin configuration, between a spin configuration and a subset C of this set of dual bonds that satisfies this crucial condition that the boundary is empty. Okay, and we have seen this correspondence. Okay, so we start from sigma, and then we find which bonds are unhappy, and for each unhappy bond we draw dual bonds to get this. Okay, and if you forget about all these spin configuration, you just get this C. Okay, and so we start from a spin configuration on these black sides, and then we got definite construction, and we get unique set C, subset C of BL star. Okay, so but I say one-to-one correspondence, so we have to start from here and go here. But it's again trivial. You can do the reverse. But be careful. This is possible only because we are treating the plus boundary conditions. Okay, in the plus boundary condition case, we have all these plus outside. Okay, to begin with. And if you do not cross this thick green thing, bond that belongs to C, the spin is the same. So here it's plus, here it's plus. But whenever you cross this thick green thing, then the spin should flip. So here it's minus. Again, plus, plus, plus. Here minus, 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 plus, 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 minus. Okay, so I didn't cheat. I didn't look at the left thing, but I could recover precisely the spin configuration here. Okay, by only knowing that we have this thing which forms the boundary, and also knowing that we have plus at the boundary. Okay, so I think you're convinced that we have a one-to-one correspondence between spin configurations and these sets of dual bonds. Okay, that satisfies this crucial condition. And now, so we can write down the stochastic geometric representation of Z. Okay, so we look at equation 1 in 5. So P5(1) is this. Z is, well, this should be 1. Sorry. It should be 1, 2. Okay, so this is P. Oh, this should be 2, but anyway, let's go this one for the moment. So so we have this representation. So here we have U. Okay, but I claim that the size of U is equal to the size of C. Okay, well, I think it's clear because from the construction. So for each unhappy bond, we have this bonds in C. Okay, so their number is exactly the same. So instead of summing over all possible spin configuration, we can sum over all possible subsets of BL star that satisfy this condition. Okay, and again we have this not very important factor here. So now we have totally forgotten about the spin, and this is another stochastic geometric representation of Z. Okay. And I think you have already noticed that this is surprisingly similar to the representation that we have seen in part 4. So this is good old part 4. So here we were treating Z beta 0 for the periodic boundary condition. But here again we have this factor. We can forget about this. The important thing is this. We have sum over all subsets of B, the set of bonds, which satisfies again the same crucial condition that the boundary is empty. And so we have this weighted sum over all stochastic geometric object. But this geometric object is a collection are collections of loops like this. So it's really it's not only similar. This is exactly the same as here. Of course, we live in the dual world, but it's essentially it's the same. Okay, and okay, now I can just proceed to prove our main lemma, but this is such an interesting topic, so I cannot help discussing this. So this is just a side remark, but this leads us to a very interesting observation called the self-duality of the two-dimensional Ising model. Okay, so I say exactly as in part 4, P5-4. So I don't know, but anyway, P5-4. Oh yes, this one. Okay, exactly as in this thing. So we can do the same thing for free boundary condition. So for the free boundary condition in L plus, for some reason, I think you know the reason, I can repeat the same procedure and write down the stochastic geometric representation of this partition function. Again, we have this irrelevant boring quantity and boring factor and this sum here. So here the weight is hyperbolic tangent, but here anyway we have the sides, the number of bonds, and okay, so bonds satisfy the set of bonds satisfies this crucial condition. Okay, and this is of course very similar to this thing, okay, or the same as this thing, because as I said, BL star is identical to BL plus 1. Okay, so if we identify under this identification, this is exactly the same as before, but of course the factor is different. Here we have hyperbolic tangent beta, here we have e to the minus 2 beta. So this motivates us to define beta star, which is a function of beta, as a number, as a quantity satisfying this relation. Okay, so with this relation, if you consider this z free at beta star, then this is exactly equal to e to the minus 2 beta. And now this part is really same as this. Okay, so this is equal to this, so this leads to this equation. Okay, this one is so you just bring this here. And for this here, you just bring this here. And then this thing equal this thing, the other thing in the previous page, leads to this exact identity. Okay, beta and beta star are related by this, and this combination is exactly equal to this. Okay, now I take the log of everything and divide by everything by L square, and then take the limit in which L goes to infinity. Okay, then here it converges. So this we have to take into account of these boring things, and this leads to this. So probably I made a mistaken calculation, but something like this. Anyway, so what we obtain is this exact identity for the free energy density. Oh yes. Here we have plus boundary condition. Here we have minus free boundary condition. But in the infinite volume limit, we have this universal free energy density. Very nice. So this free energy density in the infinite volume limit and with h equals 0 satisfies this very, very non-trivial identity. Okay. And so this is an exact relation that relates a free energy at high and low temperatures. Why is this? Well, look at this thing. If you let beta approach 0, then this approaches 1. This means that beta star approaches infinity. Or the same thing. If you let beta go to infinity, then this gets smaller and smaller. This means that beta star approaches 0. Okay, so this beta, so they really so if this guy is expressing something in very low temperature, this guy is expressing something in very, very high temperature. This is very interesting. And usually in duality, usually low temperature region of some model is related to high temperature region of a different model. But in this case, the low temperature region of the two-dimensional Ising model is related to the high temperature region of the exactly same two-dimensional Ising model. So this is why this is called, the relation is called the self-duality. Very interesting relation. And but this is not our main topic. So I just mentioned, and I have derived, I just mentioned that it's such a non-trivial relation here, but one more. So there is a very special point, which is called the self-dual point, in which beta equals beta star. They become identical. So that's defined by this. And you can solve this to find that this beta c is given by this. And actually, this self-dual point, beta c, turns out to be the exact transition point, critical point of the two-dimensional Ising model. Okay, so anyway, this was a side remark. Where were we? So we were here. Okay, so we have derived this stochastic geometric representation for the partition function under the plus boundary condition and the zero magnetic field. Okay, our next task is to consider a similar representation for the expectation value of sigma u, because this is a quantity that we are interested in. But actually, this is not at all difficult. So now again, we consider this product. And then this leads us to this unnormalized expectation value. Okay, so, and everything is the same, actually, as before, because we didn't do much here in this derivation here. So what we have done is simply we have just rewritten this Boltzmann factor like this and pull this out and rewritten everything. So we have just rewritten this Boltzmann factor in this form. That's basically what we did. And then, but we have rewritten this sum over all spin configuration as a sum over all C. But this is just from this one-to-one correspondence. So you can do exactly the same thing with sigma u here. Okay, and the result is here. So we have the same prefactor, the same summation, same thing, and this is extra thing. So sigma u always remain here, and it's here. And what is this sigma u c? Well, now we have lost, we don't have any spin configuration sigma here, so we have to sort of recover the value of sigma u from this this set C. But you know, as we did before, if you know C, you always recover the spin configuration. So you can always uniquely recover the value of sigma u c by looking at C. So this is what we put here. Okay. Now, so in order to get this, you divide this by z, of course. And then we know the stochastic geometric representation of z, which is this is z is this prefactor times this thing. So this is z. So we have these prefactor in both cases, so we can just get rid of them and rid of it. So we have this expression. So this is here. And so this is an exact expression for this expectation value, and we rewrite this like this. But this is again trivial. So let me just regard this part as PC. So let me just write this part as P of C. And then this becomes this. I mean, this sum is this. Okay. And so PC is by definition this one. But we can regard this as the probability that the set C appears. Why? Well, because, well, this really shows. And also, this is always non-negative. So, and if you sum this over all C, then you just sum it, but you get the same thing. So this is 1. Okay. So this is really the probability. You can interpret this as the probability. So this is a stochastic geometric representation of this sigma, right? So we are now dealing with the statistical mechanics of shapes, these C's. So a bunch of C's appear with this weight, and we are averaging this quantity. Okay, so I think we're close to the goal, but we still need 1 or 2 interesting ideas. Okay, so one thing is how do we lower bound this thing? For this purpose, we define 2 sets of C's. So this curly C of L denotes all possible C, which is a subset of BL star and satisfies this condition of empty boundary. Okay, so and this is isomorphic to the total spin configuration because of the one-to-one correspondence. But anyway, you don't have to care about this. So this CL, curly CL, is something we have already seen many, many times. So here, for example, if you use this notation, you can rewrite this as some like this. So this is the same as sum over all elements in curly CL. Good. And I also define this curly CUL, which depends on this site U. And this is the element of this curly CL, and with this extra condition. The condition says that this site U, particular site U, is surrounded by at least one loop in C. Okay, let's look at this. So suppose that this yellow site is U. And then in this case, this C satisfies this condition, and it surrounds. It really surrounds. Yeah, you see, this U is really surrounded by this. Okay, so now in this case, this subset C does not satisfy this condition, and it's not in this curly CUL. And so because this is our U, and it's facing these green bonds, and probably you feel like you're surrounded by these green bonds. But if you're careful, there is a way out. I mean, if you go here, 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 you can escape to the boundary without passing through grooving. Well, of course, if you're too stupid, you go through. But if you're clever enough, you can escape to the boundary without passing through these green bonds. Here, no matter how clever you are, you always have to go through green bonds to go to the boundary. Okay, it's a crucial difference. Okay, so so these are well-defined things. Okay, and now let's examine the value of sigma UC for these configurations. So first, suppose that C is not in curly CUL. So this kind of case. And then, in this case, I claim that sigma UC is always 1. Why? Well, I think we have already seen this trick. So if C is not in curly CUL, you can reach the boundary. You can go to the boundary from U without crossing these green bonds. Okay, so it means that you can reach the boundary without going through a spin flip. So no spin flip, no spin flip, no spin flip, no spin flip, and you reach the boundary where the spin is plus. Okay? This means that you originally started from plus. Of course, it's clear from this picture, but it's in general true. So in this case, we can conclude that sigma UC must be 1. Okay, then what happens if C belongs to curly CUL? Well, you might say that, okay, it must be -1 from this picture, but we have to be careful. I mean, the definition is that it's surrounded by at least one loop. So it may happen that this U is surrounded by 2 loops like this. And in this case, U is really surrounded by this. So this C belongs to curly CUL. But in this case, U is plus. Okay. So in this case, U is minus. No, I'm sorry. Sigma U is plus. In this case, sigma U is minus. So since we don't know how many loops surround U in this case, so we are not sure about this value. So in this case, basically we don't know anything. So we are sure here. We don't know anything here. But this is enough for our purpose. Now we can lower bound this quantity. Okay, so first of all, this is our stochastic geometric representation. This is exact. Okay, now this is just a trivial rewriting. We divided sum into two. So here I just sum over all C in curly CUL, and here I just sum over the remainder. Okay, but for this remainder from the previous consideration, we know that this is always 1. Very good news. And from the previous consideration, we don't know anything. We don't know anything about this, basically. So we can set this to be 1. And for this thing, we're not sure about anything. So we just say that this is, well, this is always true, since sigma is either plus or -1. So this is always greater than or equal to -1. Okay, so if you use this, this is written like this. So this is replaced by minus, and this is here. Okay, now note that we don't have sigma anymore, sigma U anymore. Okay, good. And now, of course, this is written like this because this plus this is 1. Okay, so this is simply 1 minus of this thing, and but this is the same as this. So this becomes 1 minus twice this. Okay, so this is basically the probability that C belongs to this. Oops. So something went wrong. So but anyway, this becomes 1 minus twice this thing. Okay, and this is nothing but the probability that this C belongs to this curly CUL. Okay, so this is a probability that if you pick C, then it surrounds U at least once. Okay, so so we want to lower bound this quantity. So our final task will be to upper bound, to bound this quantity from above. Okay. So for this purpose, we take any C, that's the set of dual bonds that belongs to this curly UL. Okay, so by definition, we observe that there is always a contour, a loop, and by a contour, I mean a loop with no self-intersection, gamma, which is the subset of C, and that surrounds U. Okay, so I think this picture will show you. So this is U, and this is our C. So in this case, U is surrounded by at least one loop. So I just pick up this loop without self-intersection. So of course, this can be a loop, but I insist that a contour has no self-intersection. So now in this case, this is our gamma. Okay, and so I just pick this gamma out. So there by definition, there always exists such a contour. Okay, and then I take away this contour gamma from C and call the remainder C prime. Okay, it's here. And this reminds you of the discussion in part 4, but I think this is much easier. We only have this set of loops, and I just delete one of the non-self-intersecting loop gamma. Okay, and then remainder is of course the collection of loops, and it satisfies this. If you really want to derive this, I mean we start from the condition that dc equal phi, and you also note that d gamma equal phi. And from this, you immediately get this. But from picture, it's just clear. This empty boundary means that you have collection of loops. You start from collection of loops. You just take away one loop without self-intersection. And then, of course, the remainder is just a collection of loops. Okay, so now, so C prime, okay, so C is the union of C prime and gamma. Okay, so what is the weight for this? Well, this is an easy part. So if you recall the definition of PC, which we had in page 9.3, which is, okay, this is page 9.3. Okay, so the definition is very simple. We have this normalization factor, and it's simply e to the minus 2 beta, the size of C, the number of elements in C. Okay, so in this case, the number of elements in C is equal to the number of elements in C prime plus the number of elements in gamma. Okay, okay. So the definition tells you that it's equal to this is equal to this. Very simple. Okay, so with this in hand, we try to upper bound this. Okay, so we try to upper bound this probability. So again, we need to sum over all this, but as before, we first sum over all possible contours that surrounds U. Okay, and then we sum over the remainder of C prime. Okay, and now look, C had a condition had to satisfy the condition that U is surrounded by a loop, but C prime is free from such a condition. Okay, so this condition disappears, and we only need to sum from C curly CL. But we have this extra condition here. What is this? Well, this is again similar to the consideration in part 4. So C prime is obtained from C by taking away gamma. Okay, so C prime can never have intersection with gamma. This is the condition. Okay, and I again say that I claim that this is an upper bound because by doing this we are already overcounting. So sometimes the contour is not unique, and we may take several different gammas. Okay, so in that case, we are overcounting, so this is upper bound anyway. Okay, so we have this, and again, as before, as in part 4, we try to forget about this condition here. Okay, if you forget about this condition, this means we sum over more and more c primes, but since this is a positive factor, we always have upper bound. Okay, so by forgetting about this condition, we have the same sum over gamma, and we have unconditioned sum over c prime. Okay, this is an upper bound. But look, this is very easy. Because if you sum over this, then the normalization condition tells you that this is just 1. Okay, so we are left with this very simple thing. Okay, we are left with the sum over all contours, and this is e to the minus 2 beta, the size of gamma. Okay, and well, again, something is wrong. Sorry. Okay, so anyway, this is a quantity that we wanted to bound from above, and we were able to bound this by this sum over contours, okay, over all contours that surrounds you, all the contours that's surrounding you, and here's the factor. So here's the size of the contour. Okay, and then as before, you can rewrite this in this way. So this WL is a number of the total number of contours with L bonds that surround you. Okay. And in this case, this starts from 4, because if U is here, the smallest contour that surrounds U is like this, and it contains 4 bonds. And of course, this should not be infinite, but I mean, it's easy, so we just set infinity here. Okay, and we just sum over this factor. Okay, so the remaining task is to bound this, and well, so this is a little bit more complicated than the counting of random walk, but in the remaining 2 pages, I'm going to show that this is upper bounded by this. Okay, and then please believe me, and then this thing is, we claim that this thing is lower bounded by this thing, but now we see that this is upper bounded by this. So if you plug this in, we have this, and now we plug this upper bound here to get this lower bound. And so we get this a little bit complicated sum, but it's just clear that if beta is very large, then this becomes very small. Oh, by the way, this is a familiar factor that we have seen in the very introductory part, where we discussed heuristically the Pyers argument. Okay, so we have this factor, and if this factor is very, very small, if beta is large, so large that this is very small, it's just clear that this summation is very small. Okay, and in particular, if beta is sufficiently large, this summation becomes strictly less than 1/2. Okay, it's not enough that this is finite. Okay, if this is finite in like 10, then we have 1 minus 20, so we get some negative quantity. So this must be strictly less than 1/2. And but if this is strictly less than 1/2, then we see that this is strictly larger than 0. Okay, it's strictly positive. So this is our definition. This is defined as our mu beta. Okay, and so for some beta, this is strictly positive. Of course, this is not at all optimal. You can play with this and get better numerical result. Okay, and also since this is our definition, it's clear that if you let beta go to infinity, this approaches 1. Why? Well, if beta goes to infinity, this thing becomes smaller and smaller, so this converges to 0, so this converges to 1. Okay. So that's basically the end of the proof. So the only thing we have to show is this upper bound for WL. This is very similar to the corresponding estimate for the random walk that we discussed in part 4, but this one is slightly more complicated. So let me proceed step by step. So first of all, I consider this quantity W prime L, that is the number of contours with L bond that contains a fixed site. So I forget about this surrounding U. I just fix one site and grow a contour or a loop without self-intersection from this thing. So this is now very similar to the game that we did in part 4. So first of all, this is a starting point. So there are 4 choices. And after this, we have basically at most 3 choices. But we we avoid self-intersection and so on. So usually, in many cases, the choice is less than 3. But anyway, we have at most 3 choices. And for here. And as for the final step, now this is a different point from the random walk. We have to form a loop. So if you have L minus 1 bonds, and if you're here, then your choice is unique. You have to go here. And usually, after L minus 1 step, probably you are here. And you have to go back here in 1 step. You can never do that. So in that case, you fail. But anyway, it's true that the choice is 4 in the beginning, and you have at most 3 choices here and no choice here. So it gives you this upper bound. But in this way, actually, we are double counting. This is tedious, but we are double counting the same loop in this direction and this direction. So you can divide this by 1/2 to get this upper bound. Okay, so this is W prime L. And now we consider different quantity number, which is W double prime L, which is the number of possible patterns of contours with L bonds. So we don't care where it is. We just want to count a distinct number of patterns. Or more precisely, we identify 2 contours that are related by a translation and consider them as a unique, as a single contour. So definitely we are, by doing this count, we are looking at all possible patterns. We are generating all possible patterns. That is definitely true. And actually still we are making overcount, right? We are doing overestimate. We are counting the same contour several times here because for example, if you start from here, you can grow this kind of contour like this. Okay, this is 2 by 2. But starting from here, the same point, you can grow this thing too. Or, yes. So in this case, we got this and this, but they should be the same. Okay, so if you are given this shape, you may ask which point is the starting point. Okay, so in this first game, we are fixing the starting point. So this means that this shape is counted like 6 times here. Okay, so oh, this is again a bit tedious, but anyway, this consideration shows you that this W double prime is given by this 1/L times W prime. So by using this upper bound, this is upper bounded like this. Okay, one more consideration. So now we want to upper bound this number of contours with L bonds that surround you. So now we pick one shape of contour, and so we first fix the shape pattern of the contour, and then we ask where is U, and where can we put U? Okay, you cannot be we cannot put U outside, but we can imagine that U is anywhere inside this. Okay, so once we fix the shape, we can think about many possible locations of U's, and that will count the corresponding number of contours that surrounds U. Okay, so we shall ask, what is the number of sites surrounded by a contour with L bonds? And this is an easy maximization problem, and you will find that this number of sites surrounded by this loop is maximum when this is just a squared, right square. And so in this case, L should be divided by 4, but in this case, the area is maximum. Okay, so anyway, so from this consideration, we see that the number of sites surrounded by a contour with L bonds is upper bounded by this. Okay, so this leads to this upper bound. WL, the desired number of possible contours with L bond that surrounds U, is obtained by multiplying this W double prime. This is a number of different patterns by this number of possible locations of U. And we know the upper bound for this. So we plug this in, and well, we get this. And if you compute, you get this 72. All right. So this is the end of the proof. I'm a bit tired. So anyway, we have finally proved this lemma here. Okay. So everything is done, and the theorem 5 has been proved. So this is the argument invented by Professor Pyros and made into mathematical proofs by Professor Griffiths and Professor Dobrushin. Phew. Okay, so this is basically the end. So this is part 2. So we have dealt with the two-dimensional Ising model, very standard Ising model. And in part 3, we proved that the infinite volume limit of this free energy density exists and is independent of the boundary condition. So we regarded this FBTH represents thermodynamic property of the system. So we focused on this and we tried to find non-trivial property of this. And we did, and we proved two very important theorems. So we defined this spontaneous magnetization as the right minus of the right derivative of this free energy. And we have shown that this spontaneous magnetization is vanishing in high temperature region, and it's strictly positive in low temperature region. Okay, so we do not know the exact critical point. Of course, people now know, but this argument does not tell you what happens near the critical point. But anyway, we have perfectly rigorous control of what happens here for the sufficiently low temperature region, and here for the sufficiently high temperature region. Okay, I think the proof was not trivial, but I would say that they were not very hard. And I myself think these proofs very interesting and contains not only mathematics, but contains lots of interesting physical ideas. And I hope you enjoyed this. Okay, so that's all for this mini course on, what was the title? The mini course on the proof of the existence of a phase transition in the two-dimensional Ising model. And I hope you enjoyed, and thank you very much for watching. Goodbye.